Now that I've introduced the Bode approximation, I'd like to show how we can use it to simply plot an approximation to the amplitude response of circuits, knowing their gain at one frequency and the locations of all of the poles and zeros. We'll look at some circuits that we've examined before, starting off with possibly the simplest one, which is just the resistor connected to a capacitor like this. And for that, we found that the frequency response was 1 over 1 plus j omega RC. It's quite straightforward to get this expression into the general form. Reminder, the general form is h of omega, g times j omega to the power of n. These are the zeros at 0 hertz. 1 plus j omega divided by minus z, and so on. These are the zeros, over 1 plus j omega over minus p, and so on. These are the poles. Well, here, the numerator is just 1, which means that we don't have any zeros at all. So we don't need that term, and we don't need any of those terms either. We do have a pole, however, and by comparing this term with this term, we can see that our pole, P, must be minus 1 over RC. Then all that remains is to note that G is just equal to 1, and we can get our expression here into our standard form. Right. G is 1. Expressing 1 in terms of decibels gives you 20 log 10 of 1, that's just 0. And since we have no zeros at 0 hertz, G is the gain at DC, the gain at low frequencies. So we can start our Bode approximation in this case at 0 dB. As these are going to be frequencies that are a long way below the break frequency of this pole, and therefore this pole is having no effect at these low frequencies. And our gain, being 1, just means that at low frequencies we're starting at 0 dBs. And that will carry on until we get to the break frequency of this pole. And the break frequency of this pole is going to be the modulus of the pole, in other words, 1 over RC radians per second. Once we get to 1 over RC radians per second, the Bode approximation says the full effect of the pole starts to happen. And the full effect of a pole is to decrease the amplitude response by 20 dBs per decade. So this would be heading down at 20 dBs per decade. That's it. That's the Bode approximation of the frequency response of this circuit. The actual frequency response would agree with the Bode approximation at low frequencies and at high frequencies, but in between would introduce this kind of curve. Now, how about that case where the capacitor and the resistor are the other way round? We'd have this circuit, and the frequency response of this circuit was j omega RC over 1 plus j omega RC. Again, we can derive that just simply using the potential divider equation for this circuit. Well, now we do have a 0 at 0 hertz. There's a factor of j omega in the numerator here. So in the general form, where I have to write g times j omega to the power of n times the effect of all other zeros, and so on, over the effect of all of the poles, and so on, I can see that we've got one pole, and the one pole is going to be, as before, at minus 1 over RC. I'm not going to have any zeros that are not at 0 hertz, but I do have one zero here at 0 hertz. And G is now going to have to be equal to RC. So I would have my final standard form equation as RC times j omega all over 1 plus j omega divided by the pole, or minus the pole being at minus 1 over RC, makes that into a plus. Now, for the Bode approximation, I know that the effect of a zero at 0 Hertz is to increase the amplitude response at 20 dBs per decade. The pole is having no effect for frequencies a long way below the pole's break frequency, so at these very low frequencies we're just going to have an amplitude response which is going up at 20 dBs per decade. And that will continue until we get to the break frequency of the pole, which is at 1 over RC radians per second. At that frequency, Bode assumes that the entire effect of the pole starts, and the effect of the pole is to reduce the gain by 20 dBs per decade. So above that frequency, we've got a zero, which is trying to increase the gain at 20 dBs per decade, and a pole which is trying to reduce the gain at 20 dBs per decade. And these perfectly cancel each other out. Net result, the output is horizontal. In terms of where this point is, it's usually easier to consider a particular frequency. And in this case, we can see that at high frequencies, heading off to an infinite frequency, the gain should be constant. And if we go back and look at this frequency response equation, we can see that at very high frequencies, where j omega RC is going to be much, much bigger than 1, we can neglect the 1 with respect to the j omega RC. That just leaves us with j omega RC over j omega RC. In other words, h at high frequencies is just going to be equal to 1. 1 expressed in logs is 0, so in terms of decibels, that means that 20 log of 1 is 0, that's going to be 0 dB. So that is our Bode approximation of this circuit. Once again, always label your axes with units, log of frequency in radians per second in this case. Let's do a slightly more complex one. For a more complex example, let's go back and look at this circuit again. We've been through the tedious algebra required to derive the frequency response of this before, so I won't do it again. We do have, however, another set of tedious algebra to do in order to work out where the poles are. To do that, we'll have to solve the quadratic equation on this denominator. It's fairly straightforward, if somewhat tedious. It's the standard quadratic equation formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a. Hopefully everybody is familiar with that. And if you just do the appropriate substitutions, you will end up with a 0 at minus 1 over R2C2 in this case. That isn't too difficult to see. And 2 poles at angular frequencies given by this expression here. To make any further progress, we'll have to put in some values for the resistors and capacitors. Let's put in these values. If I use these values and then substitute them into the equations on the last slide, we end up with a 0 at 159.2 Hertz. I've converted back into Hertz here because that's the axes used on this plot here. And 2 poles. The first at 14.35 Hertz. And the second at 17.65 kilohertz. The other information that we will need to use the Bode approximation is the gain at a particular frequency. We can either go back and look at the frequency response, or we can just look at the circuit and note that at very low frequencies, the capacitors will have an effectively infinite resistance, which means there will be no current flowing around this circuit. which means there will be no potential drop across this 100k resistor, which means the output will be equal to the input. So we can tell just by looking at this circuit that at very low frequencies, the amplitude response is just going to be 1 or 0 dBs. So we can start our Bode approximation plot at 0 dBs. Gain dB log of frequency in hertz in this case. At all frequencies below the break frequencies, these are the break frequencies of the zeros and the poles, by the way. I should have made that clear. The actual zero is at minus 159.2 hertz. The actual poles are at minus 14.35 and minus 17.65 kilohertz. These are the break frequencies. I'll maybe notate that just to remind myself that these are break frequencies, not the actual values of the zeros and the poles. So anyway, we start off at 0 dB at low frequency, and at frequencies below their break points, none of these zeros or poles are going to have any effect. The first one that's going to have any effect is this pole with the lowest break frequency. So the Bode approximation would say we go out to 14.35 hertz, and then this pole will start to have an effect. The zero and the other pole are not having an effect yet, but this pole is. And this pole will be pushing the amplitude response down by 20 dBs per decade. And will continue to do that until you get to the next break frequency. Well, actually, it will continue to do that forever, but the graph will continue to go down at 20 dBs per decade until you get to the next break frequency, which here is a 0 at 159.2 hertz. Now the 0 switches on and starts to try and increase the amplitude response by 20 dBs per decade. So we've now got a pole pulling it down and a 0 pulling it up. Net result, it just carries on horizontal until we get to the final break frequency, which in this case 17.65 kilohertz, and now we will have two poles pushing it down at 20 dBs per decade, but only one 0 pushing it up. Net result, it heads down again at net 20 dBs per decade. And that's it. That's our Bode approximation of the amplitude response of this network. And this is the actual amplitude response. If you compare the two, you'll see that the Bode approximation is actually very good in between the break frequencies. It's only around the break frequencies where the approximation starts to deviate from the actual result. And in many cases, where all of your poles are real, it doesn't deviate by more than 3 dB or so. And you can always get a more accurate estimate by producing your Bode approximation, straight line approximation, and then just rounding out the bends a bit. We'll be coming back to the Bode approximation later. Next time I want to start looking at what is almost the reverse problem. Starting with the amplitude response of a network, how do you estimate where the poles and the zeros are?